Have you ever wondered where that we've been called the carbon life forms? That's what we are. Where does this come from? We're now going to start looking in chemistry at organic chemistry. Now, up until now, we've looked at chemistry that looks like this. Remember, we've looked at sodium formed a +1 and chlorine was -1. Therefore, we got NaCl. We've looked at the combination of elements, basically more or less like two. I know we've had magnesium sulfate, for example, right? Where we've got an SO4 of a -2. Those are our complex ions, right? But if you remember, we've had chemicals, this character here was CH4, right? And when we did him, we said carbon has that, and we bonded 4 hydrogens onto that, right? And if you remember, we've looked at the molecular shape, we've looked at the different kinds of bonding, ionic, covalent or polar covalent, pure covalent, metallic. We've looked at those. Now, if you remember this one, all right, over there, I can't hold 4 up at the time, but we had over here our carbon atom, and we surrounded it with 4, right? And we found that they sat around it like that. And what happened was each one bonded their electron orbital shells into it. And this molecule became nonpolar because it's symmetrical. So it's not polar. So remember we looked at the electronegativities to see if it was polar or not. If it was over 2.1, it's ionic. Below that, down to 0.3 or 0.4, it was polar covalent. Under 0.3, it fell into the pure category. Some had a change in or delta electronegativity of 0. That's absolutely pure covalent, right? We're going to be revisiting some of that, but in a different form of chemistry. We went through the table or the periodic table, and what did we see? We saw, remember, metals, nonmetals. Metals give away electrons. Nonmetals took electrons, generally speaking, and then we looked at the kinds of reactions that we got with those, with acids and things like that, and we built up a general understanding of how things fit together using the periodic table. But remember we said going across, we've got hydrogen 1, beryllium 2, boron +3, carbon, well, fluorine -1, oxygen -2, nitrogen -3. What was carbon? Carbon was plus or -4. Because when we drew the diagram of carbon, the Lewis diagram, we had that, right? The outer valence electrons in the carbon atom, there was 4, remember I called them 4 parking spaces. Now, those 4 parking spaces that we had, okay, over here and over here and over here, all right, you can only stick 4 other electrons in there. Remember, whatever bonds in here created an electron pairing. So when we bonded it, right, like for example, methane or CH4, we had C, H, 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 H. Each one of these lines over here was an electron and an electron given by both parties. Covalent, sharing valence electrons. Now, carbon had the anomaly. It could be a plus or a -4. What does that actually mean for us? Well, it means quite simply that carbon naturally has an affinity, and I'm not saying electron affinity, but it has the ability, let's say it has the ability to bond with a hydrogen, which is a +1, or a chlorine, which is a -1, right? So hydrogen can actually, or carbon can actually bond with a plus or a minus, right? So carbon has got 4 possible bonding units. Generally speaking, we're going to start off by looking at H's around it. So there's the most basic one, which is CH4, which you remember was called methane. All right? The gas that you find in coal mines, responsible for many, many explosions and deaths of many miners, because it was an undetectable gas but highly flammable. Now, what happens next with carbon? Carbon actually does this. And carbon can form long chains. Carbon forms long chains, right? It's irritating when it does that, probably for you more than me. Long chains, right? So each carbon atom, but remember it's still got 4 stalks, 4 stripes around it. So we are building up here a thing that looks like this. Like that. Carbon bonds with itself, right? Now, you say, okay, that's interesting. What have we created there? We've got a carbon and a hydrogen. It is called a hydrocarbon. Its essential name is a hydrocarbon because it contains only hydrogen and carbon. That's all it contains, right? Now, you remember we had the bond over there with another carbon, and we called that a diamond. Okay? Carbon is an allotrope. Remember that word? Okay? Means it bonds in different ways. The diamond was bonded in sort of the tetrahedral structure. Then you had the graphite, which was bonded in like a layer type structure with weak bonds between each layer, so it could easily slide off one over the other. That's the product. Graphene is a single layer of that. Now, in this situation here, you have carbon bonded to carbon atoms, right, to form a diamond structure. But now we've got carbon, okay, as a large chain, and we've got carbon bonded to itself 4 times. But now what about in between? Carbon can actually do this as well. Carbon's got 4 stalks. It could also do that. There's still 4, electron there, electron there. In other words, carbon can form a single, a carbon can form a double, and yes, carbon can form a triple bond. Right? So we can form different bonds, all right? We form single bonds, double and triple bonds. I think you're starting to get the feeling that this could just explode exponentially with possibilities. In that case, you're quite right. That's exactly what it can do, and it does do. That is why the secret of this, okay, is to make sure that you know the table in the textbooks. The table that shows all of the families or the functional groups and the side chains, methyl, ethyl, propyl, etc., etc. All right? Because it relies on the IUPAC naming system. We start naming by the surname, then we add on middle names, and then we add on Christian names or pre-names, right? So what are we doing is we're looking at the basic family structures. Before we go any further though, let's just look at another issue here. We just said that we had, this is my carbon atom. Let's pretend there's 4 hydrogens attached to it, okay? So there's 4 hydrogens stuck around that thing. Now we come along and we add another carbon atom like that, which means that I've got a carbon atom, okay, a carbon atom and a carbon atom like that, and I've created now another hydrocarbon. All right, the one we had above here had 1, 2, 3, 4 of them, okay, a simple hydrocarbon with all single bonds between the carbon atoms. But the interesting thing to think of is we have got here CH4. What is the molar mass of that? Well, carbon is going to be 12, right? 1, 2, 3, 4. It's number 6 and it's number 12 on the table. Remember, keep a periodic table stuck around you at all times, right? Grab one of the books that I've got lying over here. Let's go and just make sure we've got ourselves right here. Periodic, okay? The molar mass of carbon is the 12. It's element number 6. Molar mass is 12. Okay? So what is then the molar mass of this? It is 12 plus 4 is 16 grams per mole. But now what if I've got C2H? There's 3H6, right? C2H6. The molar mass of that is going to be 24 plus 6 is 30 grams per mole. So as we go up and we add carbons, right, what happens? I know this might sound obvious, but let's just get it out the way. There I've added a third carbon. There I've added a fourth carbon. I've got now 4 carbons. The mass is increasing. What does that mean? It means that the energy we need to move it is bigger. Remember we said that in the phases, to go from a liquid to a gas, you had to impart EK, which was a half mv squared. Look at what you're doing. You're changing the mass now. The heavier it is, the more energy you need to make it fly. Duh, right? A brick. Okay. Now, under this circumstance, it's important to realize that methane is a very light, it's only 1 carbon and 4 hydrogens, right? It's a relatively light hydrocarbon. But if I've got 8 of these, which is an octane, right, it's heavier. Heavier means that the chances are it has less of an ability to float freely as an octane. Okay? So, it's just something that we have to bear in mind as we go through this. The longer they are, the heavier they get. Okay. Now, let's just go now and say, okay, well, how do we work with this stuff, right? The first thing we're going to look at is we're going to look at a term called functional group. Okay? It's a functional group, and the functional group is essentially, I call it the family. Okay? It's going to give the surname. It's going to give the name. All right? Now, let's start off with the first basic ones. Just pure hydrocarbon. Pure hydrocarbons. In other words, it's carbon and hydrogen only. Then we're going to add other stuff onto those little stalks or stripes, right? But the carbon and hydrogen only, right? Let's first of all deal with it this way. I can have 3 like so, like that, right? There I have only got single bonds. Carbon to carbon. Okay? Can you see that in the next one I'm going to have a double bond? What I'm going to do, I'm going to just leave that guy out for the moment, if you don't mind. Sorry if you wrote it down, but that's a single bond carbon only, because we only look here at the bond carbon to carbon. This one is a double bond carbon, which means I can only have 2 stalks there. The total number of stripes around each carbon can only be 4, right? So they've got that. This is a double bond. C double bond C. Now we're going to go up and we're going to say, all right, the last one is a C triple bond C. All right, otherwise we're going to move out of the realms of this. This is a triple bond C, 1, 2, 3, C. Now remember also, the more bonds there are, the more energy it requires to break it apart. So a single bond is less energy than a double, which is less than a triple bond. Okay? Remember that from nitrogen versus hydrogen. and the kilojoules per mole that it took us to break them apart, which we have to do for them to react. Something else that we have to remember. By virtue of that fact, okay, each and every one of these, although they have similar carbon numbers, there's 2, all right, they are different chemistry because the bond between them is different. The bond of a single, a double, and a triple means they are a different group, okay? They're going to be different families. Although they're hydrocarbons, this one over here, all right, this one over here, I just want to move it down. If it's got single bonds only, we call it an alkane. This one we call an alkene. This one we call an alkyne. These here are the family names that we're going to refer. So step 1, as we're building up this methodology, we say, okay, the most important thing that we need to do is we need to say, first of all, okay, I just want to just take that. So step 1 in our process, step 1 is identify the carbon to carbon bonds. Single becomes an ane. Single becomes an ane. Double becomes an ene. Triple becomes an ine. Let me rewrite those in capitals, shall I? Okay. That becomes an alkane. This becomes an ene and an ine. So step 1 is we identify the bonds carbon to carbon, right? Then we're going to name them. The functional groups are alkanes, alkenes, and alkynes, all right? I call it the surname. The functional group is those, all right? Now, let's just look at, for those of you who like series and patterns, let's just look at something else. Let's take this guy here I've got 5. 3, 4, 5. So I'm going to complete this over here and put an H. Okay. I've just built up a very small 5-chain hydrocarbon over here. All right. Okay. Now, already you can tell me what is step 1 is look and see with the carbon bonds. They are all single. Therefore, it is an ane. The family name is an ane. The prefix, the name that comes in front, we're going to get to in a minute. Okay? In any event, this is pentane. Pent means 5 carbons. It's an ane is its surname. It's a pentane because there's 5 of them. All right? It's like wolf's son, the son of wolf. So we know it's wolf, son. There we go. Okay? As some you've got wolf's daughter, which is the wolf's daughter. Okay? Well, you all know how that works. So you got this situation, you got an ane, all right? We'll get into the groups, the naming in a seckie. But just let's have a look at something else. What about this, guys? Okay. Remember, always be careful. I often make mistakes with this. I really do. I'm too fast and I don't count. And I end up with bonds and H's where they shouldn't be. Still a hydrocarbon. Okay, hydrocarbon in as much as it is, or only carbons and hydrogen. Nothing else on the stalk, on the stripe. So it's a hydrocarbon. Now let's just have a look here. This is also single bonds. It's also going to be an ane. Okay, no, it's not pentane. Okay, but let's just look at something else. What's the molecular formula? What is the molecular formula? Molecular formula is CaCl, 2, right? So here I've got C5, H3, 6, 7, 8, 9, 10, 12, right? Look here. I've got C5, but I've got H6, 6, 9, 10, 11, 12 again, right? Okay. Now if I go up, yep, we're going to change it yet again. We're going to say, all right, 1, 2, 3. And what about this? HH. You guys getting the picture, I think, now of just how potentially confusing and complex this field of study is. Look, I've got 1, 2, 3. I've still got C5, and I've got H3, 6, 9, 12. Hold on. That whole thing weighs the same. 5 carbons, 12 hydrogens, 60, 12, 72 grams per mole. Right? What now? What is it? It's different because it's got the same number of carbons and the same number of hydrogens, but chemically they are 3 totally different things, totally different entities in entirety. All right? The first one, okay, let's just look. This is, let's just go through it here. I'll just use green. This is a long single chain, right, like that. This is a long single chain there, but it has got a side chain over here. All right? The next one down, sorry, my error there. The next one down, go back to green. You can see it's got a long chain there with 2 side chains over here. Now somebody who's smart and say, but hang on, the side chains are equal length. Spot on, you're right. It doesn't matter which way I called it because the longest chain is what matters here. Because when we're naming these, we start with the longest carbon chain. That tells us what the actual chemistry of this thing's about. Okay? This one and this one I could have used instead of the green and the blue are interchangeable, but let's say long chain there, and we've got 1 and 2 side chains. All right? Now you say, all right, fair enough, I get that. What do we call these things? They are very important things in organic chemistry. They have their own specific name. They are called isomers. Isomers, all right? An isomer has got the same chemicals, number of every atom in it. Doesn't only have to be carbons and hydrogens. It could be anything else stuck onto this chain, all right? So what we're doing is we're adding all these things on, and if the number of carbons, the number of oxygens, the number of hydrogens, the number of chlorines, or whatever we've got are all the same, they are isomers. In other words, it's got the same molecular mass, so to speak, but they are different chemicals, and they will behave differently. Why? Because they are bonded differently. Different things can attach to different ends, different energies to break the bonds and rearrange them. Okay? So it's an isomer, right? That's pretty cool. You could even have drawn the one, if you wanted to, you could have drawn it like this. I've got 5, so I've got 1, 2, 3. And what about that? Can you see? There also, so I've got 4 and 5. That's actually the same as one of the others that I've drawn. You will get the hang of these once we start naming them, and we're going to see a few of them. All right? Now, do you get different kind of isomerism? Isomerism. It exhibits, it's the property that it exhibits. It exhibits isomerism. It exhibits isomerism, which means that that particular structure, okay, can have many different solutions in inverted commas, okay? In other words, it can have lots of different ways you can rearrange the sticks and the carbon, right? Very, very simple concept, all right? All you got to remember is an isomer has got the same numbers of everything. They're just attached differently. You get different types of isomers. A chain isomer. Carbon atoms are the same number but change position to form different. A positional isomer. The functional group is located at different positions. Okay, let's have a look at a positional isomer. We've got a carbon, let's say we've got 4 carbons. Okay, and I put a chlorine on there. I could have put a chlorine over here. That is different position, same number of carbons, same number of hydrogens, still got one chlorine, but the one in black, the chlorine is on number 1. Over here, it's on number 2. Okay, don't worry about the 1s and 2s. Just note that it's in a different place, right? That's the key to this one. Now, what we're going to do is we're going to start looking at how do we name these, okay? Let's go back to some definition, all right? The functional group, we've been through there, okay? Now, let me just put on another page. Let's look at some of these, all right? Now, we've got a prefix, so we know it's an ane, an ene, or an ine, right? So we're looking at just the carbon linkages first. Step 1 is look at the carbon chain and find the linkage. Is it single? It's an ane. Double, it's an ene. Triple, it's an ine. So you look for that first. The second is we look where it is, because look at this. Yep, you got it. You could have double bond there like that, right? I am going to put in 1, 2, 3. I need 1. I generally just fill in things, and that's where it goes wrong, because we've got this, hey guys. All right. I know this will take a while because I'm doing a lot of drawing here, but we've got that. Now look at this one, CC, double bond C, single bond C. Okay, let's just put our hydrogens on here. Just for completeness, 1, 2, 3, 4, 1, 2, 3, 4, and 4 like that. Okay, so now let's examine this guy, all right? This one over here, first of all, we say, right, it's double bond, which means it's an ene, all right? That's its surname, okay? But we haven't completed, that's the first part. Then this one is also an ene, all right? But look here. This one is between there and there. This one is between there and there. Now we say, okay, step 2 is we say, aha, this is a double bond, so we are going to label it from the end closest to the functional group, which is the ene. Okay? So I say here, does it matter if I label it this way or label it the other way? No, it is symmetrical at that point. In other words, if I turn that number 2, 1 around, it's the same. So the functional group, the ene, the alkene, is in the middle, so it doesn't matter which way it goes. All right? Similarly, if you got one that was like this, I know, like that, 1, 2, 3, 4. Okay, so you've got that right. Can you see that those two are in effect the same? All we've done is we've turned it around. So now the second step is right. We identify where the the double or the triple bond is, because that's going to tell us that it's a different chemical. This one is bonded between 1 and 2. This is between 3 and 4. All right? So on the naming of them, the prefixes are quite important. This one has got 4. So what do we call it? Okay, let's look at a little table. You've got these in your books. Okay, 1 carbon, let me do it this way. Yeah, 1 carbon is meth. 2 carbons is eth. Meth, eth, prop, bute, meth, eth, prop, bute, pent, hex, and so on, right? So we've got here meth, eth, prop, bute. This is going to be 3 carbons. This is going to be 4 carbons, 5 carbons, 6 carbons, hex. So if there's 5 carbons, remember what we did. First of all, we looked and we said, right, have we got single or double bonds, right? We've got above, we've got a double bond. So we said, right, double bond. So we make it an ene. Then we say, right, how many carbons are there? There are 4. So we go to our table. So this is a bute. Okay? But now, the last thing I have to say is, look, they are different. So you have to tell me where the double bond is. So you tell me it's bute 2-ene. Oh, sorry, that's bute 1-ene. I'm thinking of the one below. This is bute 1. Okay? Bute 1. Also 1-butene. Also basically butene. Okay? Because sometimes we don't write that there. Sometimes they don't write it in the middle. Why? Because you don't write 1 times x when you do this, do you? You just write it as x. You leave the 1 out, it's implied. Okay? Otherwise, it's overload of information. Right? Now, therefore, what is this one? Well, this is 1, 2, 3, 4. It is also a bute. But where is it? It's on number 2. Now, we'll say, hang on. It's on number, if I did the blue, it's on number 2, and the red is on number 2. So it's bute 2-ene, or 2-butene. I prefer that one. Some people prefer the one underneath. I'm not sure what the going rate is at the moment. I'm pretty sure it's still the one in the middle. Okay, you'd have to check with your particular syllabus, your particular advisor, teacher, or whatever. Okay, in your particular country, obviously. Right. So bute 2-ene. Why? Is because it's on. And what about the one underneath? Okay. How do we label? We label from the end closest to the functional group. This is the functional group here, making it an ene. Okay, this is the functional group, making it an ene. All right? So step 1, we identify, right, it's a hydrocarbon. We say, right, are they single? Ane. Double? Ene. Triple? Ines. We then say, right, then we write that down. We say, right, I know it's an ene. Then I count the carbons, and I say, well, there's 4, so it's meth, eth, prop, bute. Okay, if there were 5, it'll be pent. Okay, so meth, eth, prop, bute, and it's bute. But now I have to say where the double bond is. Obviously, if it was just butane, 5 carbons, right? Let's just go through it just so that we have covered it. Let's look at this one. All right. What about this? Here we go. I'm not going to draw the hydrogens in, just pretend it's a hydrocarb. This is 1, 2, 3, 4. Okay, I need to have there, all hydrogen. So I say step 1, it is an ane. And it is 4. So it's butane. But now in this case, because the single bonds only, there's nowhere, you never say 1, 2, or 3 butane. It is just butane. Generally with the anes, there isn't a double barrel. Okay, I call this the double barrel name over here because it's like Ponsonby Smythe or Smith Jones or whatever. Right? In the next section, we're going to just carry on with the process. We're going to look at homologous series, and we're going to start putting other things onto this. Okay, I don't know. There's probably going to be about 5 in this series, maybe a few more. But we're going to do some examples as well. Okay, so chill. All we remember is we've got to know the fact that it's a single hydrocarbon and it's an ane, ene, or ine. Okay, and obviously meth, eth, prop, bute, pent, hex, sept, oct, nona, dec. Generally speaking, guys, we don't go much above an octane. Octane is what? It's a gas. It's fuel, right? It's petroleum, petrol that we put in cars is usually an octane. Okay, I'll see you in the next round. Cheers. Bye.